Okay, I want to show you some applications now of calculus to different sorts of problems, typically to find maximum and minimum values. And as is stated here in this top sentence, in this opening sentence, differential calculus can be used to find maximum and minimum values in problems that have a real life context. Okay, we're going to give you some of those real life contexts. Here's an example. I'll let you read through it. From a square piece of metal of side length 2 meters. So that's just started off as 2 meters in width, 2 meters from here to here, go all the way across. Okay, that's so 2 meters from there to there, and obviously the same this side as well, from there to there, 2 meters. So this is a 2 meter square sheet of metal that's had X meters cut out from each of the corners, so little squares of X cut out. 4 squares are removed as shown in the figure opposite, so we're just going to let these values be X. The metal is then folded along the dotted lines, I'm sure you can imagine, to give an open box with side length of height X meters. Right, so you can picture that, I hope. It's a little trough, little box. Show that the volume is given by this. Okay, so the volume of a box we know to be equal to it'll be the area of the base times the height. Now the height in this case is X, so we can go X here. Now this length here has gone from 2 meters, and we've taken little squares of X out. So if we have a look at just what's in this bit here, this will be 2 minus 2x. That's from there to there, and that's what we've got. We've got 2 minus 2x, little side lengths of 2 minus 2x now. So it'll be x by 2 minus 2x squared. That'll be our volume. So as we go about this, we just need to expand this out. Minus 8x plus 4x squared, which will equal 4x minus 8x squared, that's bracket, plus 4x cubed. And then just to rewrite it in the form that they've got it, 4x cubed minus 8x squared plus 4x. So we've satisfied part A. So part A is just about setting up an equation. What we're going to end up doing is looking at maximizing the volume, no doubt, of this box, and finding the value of x that achieves a maximum volume. So firstly is to set up an expression in V. So volume is equal to this. So obviously as we take little amounts of x out here, our volume is affected. What we'd like to know is what's the maximum value of this. Now calculus can help us with this problem. Find the value of x that gives the box its maximum volume. So maximum volume, whenever you see that word, think, well, calculus, find the derivative, make equal to 0. So for this is part A. So for part B, so we make d dx equal to 0 for the maximum value. So we'll find d dx, which is 12x squared minus 16x plus 4, and we make that equal to 0. And we find out the value of x that makes our gradient function, our derivative, equal to 0. Therefore, we know that we've either got a max or a min, and we can find out which one as the next step. So let's go through and solve this now. We can divide through by 4 firstly. 3x squared minus 4x plus 1 equals 0. Now to factorize this, I'll do this the way that most of you are doing it. Multiplies to 3, adds to minus 4. Those two numbers are minus 3 minus 1. So we've got 3x squared minus 3x minus x plus 1. And therefore 3x outside of x minus 1, that'll be minus 1 outside of x minus 1 equals 0. So it factorizes to 3x minus 1, x minus 1. So therefore my values of x that give us a 0 gradient are a third and 1. Okay, so let's think about how that works. If x is equal to 1, what would happen here? We take a meter out here and a meter out here, we'd have nothing left. So we can disregard 1, that's nonsense. That's not going to work. But 1/3, x equals 1/3, that would work. That would make this equal to 2 minus 2/3, or what's that, 4/3? So make it 4/3 width there. So we found the value of x, so therefore x equals 1/3 gives maximum volume, although we do need to verify its maximum. That's the next task, and show that the volume is a maximum for this value. The way we can do that is, as we've been doing, is just test either side. So 1/3, we can go to 0 and we can go to 1, and we can just sort of look at either side of this. So these values of x, what's our f dash x value equal to? Well, we know that at a third at 0, we go to the gradient function. We found, is this the gradient function here? Yeah, we go to this one, not this one. This is our gradient function right here. This is the one that we derived. Don't use this one because we've divided by 4 here. That's our gradient function there, 12x squared minus 16x plus 4. So put 0 in there and you get positive 4. So you get 4, and put 1 in. 12 minus 16. 12 minus 16 is minus 4 plus 4 is 0. If you put 1 in, you get 0. Now, I've used the wrong value there for my value greater than 1/3. I can't go to 1 because I've just established that at 1 derivative is 0. So that's not helpful. So let's go a bit closer to a third and choose, let's say 2/3, and put 2/3 in here. So 12 by 2/3 squared. You might want to get a calculator out for this, but that'll be 12 times 2/3 squared, which is 4/9, minus 16 by 2/3, which is 32/3, plus 4. So we'll get a read on that. So this, I've just worked this out here to be minus 4/3. We're only interested in the sign, we're not interested in the actual value. So I don't know why I put 4 there. I just want the sign. Is it positive or negative? So this is going positive, 0, negative. So therefore a max. So therefore that we verify that it is actually a maximum at 1/3. So we can give that a tick, and we can move on. We've shown that the volume is a maximum for this value. Sketch a graph of V against X for a suitable domain. So this is the time to get the calculator out. Okay, so part C is sketch the graph of V against X for a suitable domain. So let's get the calculator out, punch in 4x cubed minus 8x squared plus 4x. We get this. Now the suitable domain is in here between 0 and 1. Remember, these are my values of x. So there's no point going any higher than 1. So we just need to change our window so that we're going between, from x doesn't make sense to go any lower than, but I like to see the axes, so we'll go to -1 up to, it doesn't need to go any more than 1, so we'll just put in 1.5, so we can see a little bit of progression there. From the y min, these are the volumes, so we don't need to go any lower than that, and the volume, the maximum volume, I don't know, is it going to be about 5? Let's see how this now looks. Into that. Okay, so there we go. Yeah, I didn't need to go as high as 5. There's my volume, and we can see the maximum occurs if we went in here to find out where the maximum was. Then we would discover that it's at our point 1/3, 0.593. So if we go back in, sketch the graph of V against X for a suitable domain. Find the values of X for which V is 0.5 meters cubed. What we haven't done is found the maximum volume at this stage. So putting X equals 1/3 in, so therefore maximum volume at X equals 1/3. Therefore max volume equals, and we put 1/3 in, to 4x cubed, so 4 by 1/3 cubed, minus 8x squared, 8 times 1/3 squared, plus 4 times 1/3. We'll go ahead and do that. We can see that when we put that through our calculator, is equal to 16 over 27. So maximum volume 16 over 27, and that's in meters cubed, and that's when x equals 1/3. And so we take our little 1/3 of a meter out from the corners there. We could see this on our calculator. 0.593 is 16 over 27. 0.593. You can see that there is our max point when we go searching for that. All right, which is approximately 0.593 meters cubed. Okay, so there's an example of how we use calculus in a real life example, in this case to find the maximum volume, or the value of x in this case, that gave us the maximum volume. Don't forget, we always need to verify, looking at a point either side, and then finding the maximum is just a matter of substituting that value back in to the original equation. Okay, I'll leave this YouTube here, and there'll be one more coming up shortly, because there's one more area that we need to look at before we move into the next chapter.